Hello, my name is Lucia Fonseca de la Bella. Thank you very much for having me in Cosmology from Home. And today I will be speaking about this fantastic project called SkyPy. Before doing so, let me introduce myself. I come from a very theoretical background in cosmology. I did my bachelor degree at the Complutense University of Madrid, where I explored a little bit of the quantum cosmology. And then I moved to France and I did my master at the University of Marseille, where I had the amazing opportunity of working on effective field theory of dark energy. From there, I moved to the UK and I did my PhD at the University of Sussex on effective field theory of large-scale structure, redshift space distortions, and halo bias. After 1 year teaching, I am now a postdoctoral researcher at the University of Manchester, working with Sarah Brydon. I am a member of the Dark Energy Survey and one of the co-founders of this fantastic SkyPy project. I am working on weak lensing, but mostly on unequal time correlators, and very soon you will see fantastic research on the archive. Currently, I find myself looking for jobs and applying for jobs. Okay, enough about myself. Let's speak about SkyPy. I will walk you through its vision, its structure. I will tell you who we are, and then I'll explain the package, how we are developing the package, and finally, I'll speak about 2 key points of SkyPy, which are the driver capabilities and the research development that we are carrying out within SkyPy. Let me start with a vision. It is well understood that observational cosmology and extra-galactic observations have been limited by data access. And that's why collaborations have formed around data access. For example, Sloan, Cosmos, Dark Energy Survey. However, this is changing with the upcoming data from LSST, Euclid, WFRIST. Limiting step is access to methods, not to data. And we do have fantastic emerging methods, such as forward modeling or machine learning. Within this context, SkyPy is born. SkyPy is built around methods. SkyPy is an open source off-project high-quality Python package, and we aim to be an AstroPy affiliated package with functionality to make end-to-end simulations of the universe and to enable forward modeling and machine learning methods. But what SkyPy is not a replicate of existing code. We aim to reuse other AstroPy affiliated packages and other high-quality codes. So this is the picture of SkyPy. Regarding the structure, a board manages memberships and policies. And this is very interesting. Within SkyPy, we are organized in dynamic teams. This is to minimize permanent SkyPy structures. Imagine we have stand-up teams for every specific task on short time scales, for example, 3 months. And this works very well. And once the task is complete, the team is down and we celebrate. And also SkyPy is rewarded through citations of the package, not papers. Regarding the code structure, SkyPy package is driven by science projects. And this is very important. And I'll be speaking about this a little bit more at the end of the talk. SkyPy is done as a GitHub organization. One can open issues to request or inform of features, report bugs, and then the same person or someone else will pick up this issue and we write the code with higher standard documentation. We write the unit test and push a pull request. Then the code needs to be reviewed, and this will be done by another member of the same team, but also by a member of our fantastic, actively involved infrastructure team. And finally, we do have semantic versioning. We have staged releases, and currently on our GitHub page, you will find our version 0.2. Okay, let me tell you who we are. Let me tell you about the members of SkyPy. SkyPy collaboration is an international collaboration with experts on very different fields. The original idea is by Adam Amara from the ICT in Portsmouth. And there in Portsmouth, we have people working on galaxies and the connection between galaxies and halos. And this is Philip and Ginevra. And then we have Coleman working on infrastructure. And we have our fantastic gravitational wave team, Ian Harry, Laura Nuttall, and our two Andrews, Andrew Landgren and Andrew Williamson. Here at Manchester, we have Sarah Bridle. She is our chair of SkyPy. We have Richard Rollins, who is one of the coordinators and one of the key persons working on infrastructure. We have Nicolas Tesori, Ian Harrison, Juan Pablo working on photometric redshifts and various interests and fields. And we have myself working on growth of a structure and perturbation theory. And as I say, we are international. We have people from the US and also people from Taiwan. From the US, at the Fermilab, we have Brian Nord. He is fantastic, and he is he's our ombudsman. And we have Simon Berer from the Stanford University, working on strong lensing, and from Taiwan, Keiichi Umetsu, who is our expert on clusters. So these are the members of SkyPy. Now, I'm gonna walk you through the package, and you can find the package on our GitHub page. As I mentioned before, SkyPy intends to have some functionality to provide end-to-end simulations of the universe. So we have to code everything from very basic things like the background to more complex features like spectral or image rendering. So a bit about the features that you can find on our package. So for the background, we use AstroPy for that, for the background quantities. But then for the power spectrum features, we have mocked the CAM power spectrum. We have coded up the Eisenstein and Hu power spectrum. We have different models for the halo feeds and growth functions. More features, we have halos and galaxies with many properties. For example, for halos, you find the Press-Schechter function or the Sheff-Thurman mass function. You can do some quenching, satellite and mass quenching, and also abundance matching. Galaxies is very well developed, and we have loads of properties of galaxies. You find mass, you'll find luminosity, like Schechter function, ellipticity, sizes, redshift, spectra, many things. And just just recently, we have started working on our gravitational waves features, and you find merger rate function, for example. And also we started working on supernovae and clusters. From now on, we will be developing the Milky Way feature, writing down codes for the stars and dust. And one of the most important things is that we want to reproduce images from different experiments. For example, DES, POW, HSC, DESI, LSST, or Euclid. And finally, we'll get to image rendering and spectral rendering. So the idea is that roughly in 6 months' time, this diagram will be complete and you will be able to reproduce the universe end to end. But for the time being, you can start playing with SkyPy. How we have done this? We base our development on phase and layer-based development. We go through different phases and different layers of development. Back in January, we had our kickoff meeting, and this was very exciting because we had the opportunity to set out everything we wanted to do and how we wanted to do. But SkyPy is very flexible, and as we work, we improve everything, and we have the flexibility to change some things that we set out in January. Then we worked during our phase 1 on the intrinsic, and we had our first implementation of the power spectrum, a little bit of halos and galaxies mostly. And we had our first released in April with our version 0.1. Then we worked during our phase 2 on the observables, and we mostly developed the halo features. And then we started also working on the intrinsic of the supernovae, gravitational waves and clusters. And very recently, a month ago in July, we released our version 0.2. And now we have entered into phase 3, where we intend to develop the Milky Way features and more about the supernovae, gravitational waves and clusters. And we expect to release our version 0.3 in October. And from there on, working on experiments. And yeah, expecting more releases of SkyPy. I mentioned at the beginning that we have 2 key points in SkyPy, and one of them is the driver capabilities. The SkyPy driver runs end-to-end pipelines of functions with different dependencies, and it generates different outputs. You can find table formats or so on. And if you go to our GitHub page, you will find different examples already placed in. For example, a simple abundance matching from the Veil and Striker model in 2018, or a galaxy population from the Herbal et al. Model 2017, and also compact binary merger rates. If you go to our GitHub page, under the examples directory, you will find this abundance matching file. This is a YAML file, a config file with different dictionaries. And there is where you can write down your parameters and your different functions that you want to use from a SkyPy. In this case, for the abundance matching, you want to start setting the cosmology from AstroPy, and then your power spectrum from SkyPy power spectrum with different functions, for example, the growth function and the Eisenstein and Hu power spectrum. And this will be fed into the halo mass module and the galaxy luminosity. And you can choose, for example, the press, Schechter, mass function, and the Hubble luminosity function to draw your halos. And once you have that, you have your list of halos and your list of galaxies with its properties. And this will be fed into the halo abundance matching module. And you may choose the Veil and Striker function. The output, once this config file is run within the SkyPy driver, will be a table, and you can plot that. And this is an example where you have these very simple abundance matching. You have your halo mass and your galaxy luminosity, and this is just simply telling you that there is this relationship where you expect that your brightest galaxy will be sitting in your most massive halo. So this is what SkyPy can do, and much more. Once everything, all this diagram that I showed you earlier is developed completely, you will be able to run a simple config file in the SkyPy driver and have your universe, your end-to-end simulation of the universe. And this is fantastic. That being said, the other key point of SkyPy is the research development that we are carrying out. SkyPy, as I mentioned, is driven by science projects. On our GitHub page, you'll find the public repository called SkyPy, and you'll find all the features that I mentioned in the diagram. However, there is also a private repository where we are developing research projects. The idea is that if you want to develop a research project, science project within SkyPy, and if you are a member of SkyPy, you can do it. And all these projects will fit this SkyPy public repository. So there will be new features coming from these cutting-edge science projects. So the advantage of this is, if you do it within a SkyPy, SkyPy can help you. It can help you developing infrastructure or prioritizing some modules and some features that you may need for your project. Currently, we have 4 fantastic projects going on. We have the Galaxy Forecast by Philip Sodek. We have the Projected Ellipticities by Nicolas Tesore, Cluster Weak Lensing by Keiichi Umetsu, and the Dark Sirens with H1 Tracers by Ian Harrison. And much more to come, so let's wait and see. All these new features will be available in the public repository once this is complete. But if you're not a member of SkyPy and you still want to contribute, you can. SkyPy will be accepting external contributions. That being said, let me briefly summarize what SkyPy is. SkyPy is a legacy project. SkyPy is an open source, high quality Python package driven by science projects and aims to be an AstroPy affiliated package that do not replicate existing high quality code, with functionality to make end-to-end simulations of the universe that will enable forward modeling and machine learning methods. And what is next? We aim to release our version 0.3 in October this year, and we are currently applying for funding. But more interestingly, I have said SkyPy is a legacy project. SkyPy is not only a Python package, it's not only about science, it is also about equality, diversity, and inclusion. And we have plans to do very interesting projects along these lines. All right, so now it is your turn. Now open your terminal. You can download and install SkyPy. You can do pip install SkyPy. You can do also git clone or repository from GitHub. And then use your favorite Python shell. You can use IPython or Python or a Jupyter notebook and start playing. Import SkyPy. And coming very soon, Condor install SkyPy. Thank you very much for your attention. I hope you enjoyed.